This lecture deals with the research and development based semi-endogenous economic growth model and is based on the influential article of Chet Jones in 1995, published in the Journal of Political Economy. A textbook treatment of this can also be found in Chapter 5 of the book by Jones and Vollrath, Introduction to Economic Growth. Up to now, in the Roma model of endogenous growth, the population size of a country or of the technology leaders in common had a positive effect on economic growth. However, this is not what we see in the data, cross-country data on the population size and its effect on economic growth, and also not on data over longer periods of time and how changes in the population size affect long-run economic growth. More importantly, perhaps, the model also suggests that an increase in the number of scientists should raise long-run economic growth. And on the next slide, we will see that also this implication clashes with empirical evidence. In this chapter, we will now see a modification of the knowledge production function in the Roma model that was proposed by Jones in his 1995 paper. And this modification basically eliminates this strong scale effect. We will see that it replaces it by a weak scale effect, actually. But this implication that is not consistent with the empirical evidence vanishes by this modification. In addition, this modification also makes the knowledge production function more realistic in the sense that it can capture a wider range of parameters and also some aspects that the Roma endogenous growth model did not capture in its original form. In this figure, we see the number of scientists and engineers in the United States starting from 1950 up to 1988 actually. So that's when the data ends, and this data is taken from the website of Chet Jones. Now, what we see here is that the number of scientists went from a bit less than 200,000 to a bit less than 1 million actually over this time frame. And that means that there has been a huge increase in the number of scientists over this time period. Now, by implication of the Roma framework, where the production of technologies depends positively on the number of scientists without diminishing returns in the stock of knowledge or in the number of scientists, this would imply actually a huge increase in the growth rate of total factor productivity. Now, what does total factor productivity growth look like in the United States? Now we see this here with the dashed line and drawn on the right-hand side here on the vertical axis. Now we see here that if at all, TFP growth even decreased over this time period. So this model is then not really consistent with the implications that we see in the data. Now, what about Germany? Probably it's different in Germany, but also here we see that the number of scientists and engineers increased quite a bit since the 1960s, but total factor productivity growth did not. So therefore, the model clashes in its original form with the stylized facts, and we need a certain modification. The modification that Jones introduced is the following. So at the firm level, the knowledge production function in the research sector is still rather similar as in the Roma model. So the change in the stock of technologies depends positively on the number of scientists employed, LA, and the productivity of these scientists, delta bar. But this productivity now is only given at the firm level, but at the aggregate level, it depends on the stock of technologies and on the number of researchers, as we will see in a minute. Before we get to that, however, we note that from the perspective of the firm, the knowledge production function has constant returns to scale, so it's linear in the number of scientists employed, and the firms take the productivity parameter delta bar as exogenously given. However, at the aggregate level of the economy, delta bar itself depends first of all on delta A, that's the productivity of scientists as previously, so the higher delta A is, the more productive scientists are. And now we have intertemporal knowledge spillovers again. So the stock of technologies raises future research productivity, but not anymore as in this basic Roma model 1 for 1, but with an exponent phi that is smaller than 1. So as compared to the Roma model, the intertemporal knowledge spillovers are now weaker. In addition, we have an additional parameter lambda, and this additional parameter lambda measures the extent of duplication externalities. So what we have here is if lambda is equal to 1, then the number of scientists here drops out. But if lambda is smaller than 1, then basically we would have a negative exponent here. So LA would also show up in the denominator of this expression, such that the more scientists that are employed, the more likely it is that they develop the same idea or something like that. So it's a stepping on those externalities of scientists. So this means we have two additional parameters now in the Jones model, phi, which is smaller than 1 and therefore captures a much larger range of plausible parameter values than in the Roma model, where it was implicitly assumed to be equal to 1, which is a knife edge condition. So the parameter had exactly one number basically, and this is very unlikely that in reality exactly this parameter restriction is fulfilled. And lambda itself is the inverse measure of this stepping on those externalities. So the higher lambda is, the less likely it is that researchers are stepping on each other's toes. And this additional parameter, as we will see, makes it kind of easier to calibrate the model, and it also captures a realistic feature, namely that scientists work on the same idea in reality. So overall, we have this expression as we had on the previous slide. The parameter range for phi is that it has to be between 0 and 1, and the same holds true for lambda. The positive externality of A is again in standing on the shoulder of giants externality, and the higher phi is, the more productive future research gets when technological progress occurs. But as I said, it's weaker than in the Roma model, so there is no linearity in A anymore. And that's actually the modification that eliminates the strong scale effect. It's not so much the extension of lambda, which one might think at first, because this introduces a non-linearity with respect to the number of scientists. And since the number of scientists is related to the scale effect, one might think that this eliminates the scale effect. But actually it's that we get rid of this linearity here that also gets rid of the strong scale effect as compared to the Roma model. So the negative externality on LA, this stepping on those externality, mainly makes the model more realistic and allows for a better calibration. And it makes the model more realistic because it allows for the cases that we have here, that two researchers might develop the same idea, and we had this frequently in human history. For example, Leibniz and Newton both invented calculus. Solow and Swan both invented the Solow-Swan model approximately at the same time and independently of each other, and Bell and Gray both invented the telephone, but Bell was a little bit luckier or more successful because he filed the patent a few hours before Gray, and therefore he is credited today for the invention of the telephone. If we put things together and plug in the expression that we had on the previous slide, the delta bar, into the knowledge production function, so we take this expression and plug it in here, then we arrive at this expression here. And then we can divide by A, because that by definition gives us on the left-hand side the growth rate of A. So the growth rate of total factor productivity, or the growth rate of the stock of technologies. Now we see here on the right-hand side, A actually only appears to the power of phi, and phi is smaller than 1. In the Roma model, it would just drop out on the right-hand side, but here in the Jones model, we have that it appears in the denominator to the power of 1 minus phi, actually. So what this means is that as the stock of technologies grows, the growth rate would ceteris paribus decrease. So as long as there is no counterbalancing effect, the economy would converge as it grows to a situation of stagnation, where the growth rate of technologies becomes 0. What we have here then in the Jones model as a counterbalancing effect is that we allow for population growth and therefore also for growth in the number of scientists, such that the numerator is also allowed to grow. And for this situation, we will now derive the balanced growth path. Before we do this, we again have to note that the growth rate of per capita GDP is the same as the growth rate of technologies. So if we derive a balanced growth rate for the stock of technologies, then we also have a balanced growth rate for per capita GDP. Well, so the population, as I said, grows at the population growth rate n. And this means that we have a differential equation that describes the evolution of the population and of the workforce. And as long as the fraction of people working in the research sector is constant, then we will also have that the number of scientists grows at the same rate as the population growth rate. And this is the only feasible solution actually in the long run, because if the fraction of scientists were to grow, then we would converge to a situation where everybody is a scientist in the end, and if it were allowed to shrink, then we would converge to a situation where there are no scientists in the economy. So for a balanced growth path, we would need a constant fraction of the population working in science, and this can be solved for in general terms, but here we will just assume that it is a constant fraction that is given. Now we can proceed by applying a trick that Jones used in his framework to derive the long-run balanced growth rate. And this trick is basically to recognize that if the definition of a balanced growth path applies, then this means that the growth rates stay constant. Well, and if the growth rates stay constant, that's nothing else than the statement that the growth rate of the growth rate is equal to 0. So what Jones does is that he computes the growth rate of the growth rate of technologies. So he takes expression number 1 here and calculates the growth rate of gamma A. Now, how can we calculate the growth rate of this expression? Well, we take the logarithm and then we take the derivative with respect to time of the result, because the derivative with respect to time of the logarithm of a variable in continuous time is by definition the growth rate, as we already know from other lectures. So if we do that, if we take the logarithm of this expression here, then what we get on the right hand side is the logarithm of delta A, the first term here, plus lambda times the logarithm of LA, that's the second term here. And now since this term appears in the denominator, we have minus 1 minus phi times the logarithm of A. So all these calculations basically follow directly from the rules of applying the logarithm. And in the next step, we take the derivative with respect to time. So then we have by definition on the left-hand side the growth rate of the growth rate of technologies. And we know that along a balanced growth path, this has to be 0. The growth rate of the growth rate has to be 0, because by definition of a balanced growth path, the growth rate itself is constant. So we know that this expression here, the time derivative, has to be equal to 0. Now, delta A is a constant. It's the productivity of scientists. So if we take the derivative of the logarithm of a constant, the result is 0. Here we have lambda, that's again a constant, and the time derivative of the logarithm of the number of scientists. Now, as we know from the previous slide, the growth rate of the number of scientists is n. So that's the population growth rate. So we have here as the second term lambda times n. And finally, we have here 1 minus phi times the logarithm of A. So the logarithm of A, if we take the time derivative, that's gamma A, the growth rate of technologies. So it appears again on the right-hand side. Here it cancels out due to the calculation, so it disappears, but here it appears again. And now we can reformulate the equation such that it yields an expression for the growth rate of technologies. So we bring this to the left-hand side and divide by 1 minus phi. And what we get in the end is that the growth rate of technologies, which is equal to the growth rate of per capita GDP, is a function of the population growth rate. So that's the growth rate of the number of scientists now, then and the parameters of the model. the measure for the stepping on toes externalities. So the higher it is, ceteris paribus, the higher would be the growth rate, because then it's less likely that researchers work on the same idea, so that research effort is wasted. And if phi is higher, that means intertemporal knowledge spillovers are higher. And in this case, it's also, of course, intuitively clear that the growth rate would be higher, because the intertemporal knowledge spillovers work to increase future research productivity. Now, the important thing is that the strong scale effect has vanished. So the population size, or the number of scientists, does not show up on the right-hand side. So this means that the growth rate does not depend anymore on the number of scientists or the population size, but on the growth rate of scientists. So you get a constant growth rate of the economy if you have a constant growth rate in the number of scientists. And now this is much more consistent with what we see here in the data. So we have constant growth in the long run of the number of scientists in the United States, and also in Germany for that matter. But at the same time, the growth rate of total factor productivity does not increase, but it stays constant. And basically, one could argue that it stayed constant over the very long run. So if at all, then it decreased actually slightly, but definitely it did not increase as the Roma model, or the strict formulation of the Roma model would imply. So that means that this result is more realistic, or fits better to the empirical evidence that we have. And recall that we talked about the modeling cycle in the introduction of what an economic model is. So this would suggest that this reformulation of the model made the model better in explaining the stylized facts. We will see later on, however, that the weak scale effect still does not conform with empirical evidence, and therefore we have to take another round in the modeling cycle to improve the framework even further. So now, to summarize, the population size has no effect on long-run growth, so the strong scale effect has been removed. However, the population growth rate now has a positive effect on economic growth. This is the weak scale effect. And we will see later on how we can also eliminate the weak scale effect. In such a model, economic policies such as research and development subsidies would have no impact on the long-run growth rate. That's in contrast to the Roma framework. In the Roma model, a subsidy on research and development actually leads to a shift of labor from the production sector to the research and development sector, and this shift increases the growth rate of total factor productivity permanently, and therefore also the growth rate of per capita GDP permanently. Here, however, this is not the case. The long-run growth rate does not depend on the share of the population working in the research and development sector, and therefore a subsidy on research and development cannot permanently increase economic growth. That's the reason why this model is called a semi-endogenous growth model, because the rate of technological progress is explained within the model itself. In that sense, it's an endogenous growth model. But the growth rate itself cannot be affected by economic policies. It's really just given by a collection of parameters that cannot be influenced by policies. And that's why the semi-term comes in. So the growth rate is solved within the model itself, but only depends on parameters that policy cannot influence. And therefore, this was the reason why the framework was called the semi-endogenous growth model. Now, what's important to note is that the growth rate that we've seen is only the long-run balanced growth rate. There is also a transition phase in the model, and during this transition phase, it's much more akin to the growth rate of the Roma model. So during the transition phase, the share of the number of researchers would matter for economic growth. And that means that also research subsidies would influence the economic growth rate during the phase of transition. And the important thing now is that the transition period can last for quite a long time in these types of models, and it depends particularly on the parameter phi, on the extent of intertemporal knowledge spillovers, how long the transition phase lasts. The higher phi is, the longer the transition period will last. And for a high level of phi, you could have a situation that you simulate the model even over decades, even up to a century, and you would still in the end have discernible differences between the transition growth rate and the long run balanced growth rate. So the important takeaway here is that the transition period can last for quite a long time, and if you simulate such a model, you would see this. Now we come to an important aspect, and that is that we have now a positive implied correlation between population growth and economic growth by means of the semi-endogenous growth model. Now this is in contrast to the Swan model. In the Swan model, we've seen that an increase in the population growth rate actually reduces per capita GDP growth during the transition to the new steady state by means of the capital dilution effect. But it not only stands in contrast to the Swan model, but also to empirical evidence, which we will see. Now, what does the empirical evidence tell us? Well, basically, before 1850, there was indeed a positive correlation between technological progress and population growth, and between per capita GDP growth and population growth. This was shown in a paper by Michael Kramer in 1993. However, after 1850, this hypothesis of the semi-endogenous growth model is not anymore supported by empirical evidence. And if at all, anecdotal evidence would tell us that most technologically advanced countries nowadays have a rather low population growth rate. So over the last decades, those countries with a lower population growth rate actually performed better in terms of per capita GDP growth and in terms of productivity growth. In addition, although population growth slowed down quite a lot, productivity growth over the long time horizon is still remarkably constant to some extent. And particularly, especially poor countries have a very high population growth rate typically. So think about, for example, Nigeria versus Germany. Nigeria has a very high population growth rate, but per capita GDP growth has been rather low over the last decades, and exactly the opposite holds true for Germany. So this indicates to some extent that we cannot capture with the Jones framework everything that's going on in modern knowledge-based economies. In addition, if we look at cross-country data more systematically, then we would see a rather negative correlation between per capita GDP growth and population growth. So here we have per capita GDP growth on the horizontal axis and population growth on the vertical axis for all the countries in the World Development Indicators database, for which we have data for the year 2015. Where some outliers were corrected, so they were dropped because they had very high growth rates of more than 20% in this particular year, or very low growth rates of less than minus 10%, for example. Now, what we see here is that it seems to be the case that if at all there is a slightly negative correlation between population growth and economic growth, and this would not be consistent with the prediction of the Jones framework that we've just seen, this positive correlation between population growth and economic growth. Now, what could be the reason for this inconsistency between the model implications and the cross-country data that we see? And one plausible explanation is that the model disregards the role of human capital or education in the production of research and development. So we know that in reality, highly educated researchers and highly educated scientists actually move the research frontier forward. So it's not the sheer number of people that matters, but it matters on how well educated people are and how likely it is that a country manages to put a large number of highly educated people into the research and development sector to some extent. So what one would need to introduce into the model is an education decision or a framework to explain human capital accumulation. And we will do this in another course, basically, where we introduce into the semi-endogenous growth model the possibility for human capital accumulation and for purposeful choices in educational investments. And we will do this basically by means of the quality-quantity trade-off, where the mechanism is the following. If a family has many kids, then it's less likely that each child can go to university or can get the best education that is possible because there is the budget constraint at the family level. And if the family has fewer children, then it's more likely that these children can go to university or to the best universities because there are just fewer of them and therefore more resources available for the education of each child. Now, this quality-quantity trade-off at the family level is very well established from an empirical point of view and also theoretically in the family economics literature. But there is also a trade-off at the aggregate level that relates to the teacher-pupil ratio at school. If the population growth rate is very high, then ceteris paribus, given a certain amount of investments in education at the country level, the number of teachers per pupil will be lower. So the investments in terms of resources per child in education will be lower. And also this mechanism is a quality-quantity trade-off at the aggregate level. And overall, these quality-quantity trade-offs at the family level and at the aggregate level can translate into a situation where a reduction in population growth actually goes hand in hand with an increase in human capital accumulation, to the extent that the increase in human capital accumulation even overcompensates for the decrease in the population growth rate when it comes to the total amount of human capital that is available in the production of new technologies in the research and development sector.